All right, this is going to be a review of problem 3B.3, laminar flow in a square duct. So, square duct extends in the z direction, for length L, square is a cross section bordering lines x equals plus minus b and y equals plus or minus b. Colleague gives you this velocity profile, which you think is probably wrong. So basically, we're going to verify this profile by first deriving an unsolved differential equation with derivatives that are going to have, so like the second derivative of vz with respect to y and second derivative of vz with respect to x. It's going to have those in the expression, and then we're going to take the derivative of the partial derivative of this equation with respect to y and respect to x twice, and we're going to get second derivative of vz with respect to x and second derivative of vz with respect to y from this equation, and we're going to plug it into that other equation, or to the momentum balance equation that we get that's like unsolved with the two partial second derivatives in it. We're going to plug the derivatives from here into that, and then we're going to verify that the equation is true for all conditions, basically. So we'll get into that, and you'll see that this equation is not true for all conditions, basically. All right, so let's get into it. First, this is the model that we'll use for the duct. We'll assume that duct is vertical. So first, equation of continuity for Cartesian units. Equation of continuity for Cartesian. So it's this equation here. It's page 846, table B4. And this is just to basically just eliminate some, basically be able to say that Vz is not dependent on Z, basically. So first part is that steady state, where we're in a steady state system. So dρ/dt equals 0. There's no x velocity because the air is just going up. There's no y velocity, again, because the air is just going up. And this equation stays, but you can take the rho out of the equation, and it basically just says that velocity in the z direction is not dependent on z. All right, so now we got the equation of motion in terms of rho and viscosity. And we're not using this equation because it's Newtonian fluid. And if you did you could use this equation, but you would have to basically plug in all the definitions for the shear stresses and normal stresses, which is really annoying. So we can make this simplification for Cartesian, taking density and viscosity as constant, and it just makes deriving this equation easier. So we're looking at the velocity in the z direction, so we're looking at b.6-3 because rho gz. Basically, that's how I figure it out most of the time. All right, so that's this equation. dvz dt is 0, and that's because there's no velocity, or not. It's because of their steady state. Vx equals 0 because it doesn't exist. Vy equals 0 because it doesn't exist. dvz dz equals 0 because of the equation of continuity to prove that. And again, d squared vz dz squared equals 0 again because of the equation of continuity. So all you're left with is this, and we can combine these two terms into this definition here. All right, here's the derivation for the modified pressure equation. So basically you have this standard equation: modified pressure equals pressure plus rho times g, or density times g times the height at that pressure. So which is what this example gives you for this equation. Z increases with gravity, and in our coordinate system, Z increases against gravity. So that's going to be important, and that's going to mean that we're going to have to modify this equation, and I'll show you why. Yeah. So with this equation, we can see that the the um, the modified pressure P0 equals P0 plus rho G times L, and yeah, so PL is always the pressure that's like farthest away from the z-axis. So it's like L always extends with the z direction, basically. So, but the height at P0 is still L because height always increases from bottom to top. It increases against gravity, like what you would think normally. So height increases this way, but the z direction and like the direction of L increases with the z coordinate. So it's kind of confusing, but yeah. So the modified pressure P0 equals P0 plus rho times G times the height at P0, which is L. So yeah, the length extends in the coordinate direction regardless of gravity. So in our system, Z increases with height. So as you can see, or is it? Yeah, Z increases with height. So that's opposite of this derivation with this system here. So yeah, let's see. So yeah, so that means that for us, delta P0 or modified pressure 0 equals P0 plus rho times G times 0. And that's because the height at P0 is just 0. So we can see that this isn't the same, like this doesn't give the same answer as this equation here for the same coordinate. So we want it to give the same answer, basically. So we're going to have to flip the sign of the equation, and we're going to have to say delta, or not delta, modified pressure equals P minus rho times G times H. And again, that's because these coordinates are flipped. So going back to the equation that we're trying to solve for, so we're just going to we're going to put this in terms of modified pressure. So yeah, negative dP dz equals the final pressure minus the initial pressure divided by the final position minus the initial position. And that's PL is the final pressure, and P0 is the initial pressure, and L is the final height, and 0 is the initial height, or the initial z coordinate, whatever, plus rho gz. And then we're going to derive the modified pressure at each point. Modified pressure 0 equals P0 minus rho G 0. So that's just P0 basically. And PL equals PL minus rho G times L. So now you want to subtract the P0 minus PL so you can like get something similar to this P0 minus PL. And you get P0 minus PL equals rho times G times L. And then basically just divide both of these sides by L, and you get modified pressure 0 minus modified pressure L to all over L equals P0 minus PL divided by L plus rho gz, and that equals this expression. So like when you distribute this negative sign into here, or well actually, yeah, it shows the distributing the negative sign here. So you distribute the negative sign here, these two terms just basically switch, and it becomes P0 minus PL all over L plus rho gz. And we can see here that equals modified pressure 0 minus modified pressure L divided by L. So yeah, that's the derivation for modified pressure. But so you just rewrite the equation, basically inserting this definition for these two terms here, and you get that. So this is the equation where you're going to plug the derivatives into from this equation. So you take the derivatives with respect to x and y twice for this equation, and then you plug them into this equation, and you prove that the equation is not really valid. So this is the equation from the problem. This equation here. And so we want to find the derivatives. We want to find these two derivatives. So first we're going to basically just break the equation up to make it easier to look at. And we're going to take the second derivative with respect to x first. So this is just partial derivatives. It's pretty easy. So you basically just treat every variable that's not the variable of interest, which in this case it's x, as a constant, and then you just take the derivative. So it'd be 0 minus 2x over b squared plus 2xy squared over b to the fourth. And that's what you get. And then you take the derivative again, and you get 2 over b squared plus 2y squared over b to the fourth. And yeah. All right, I guess I flipped them around because it's just a mess over. Yeah, that's what you do. You do the same thing with y as well. So again, it's the derivative of this with respect to y. So it's 0 minus 2y over b squared plus 0 plus 2y over b to the fourth. And yeah, that's what you get. And the same thing again to get the second derivative, and then you insert these definitions into this equation, and then we're just going to do some simplifying basically. Yeah, so doing that, condense terms and divide by viscosity. So I think here, what do I do? Yeah, I just put these two terms together. I put these two terms together, and I put them all under one pressure conglomerate term, basically. But I was doing this one. Okay, yeah, the mu out here. That's divided by that. Okay, so now distribute b to the fourth into the parentheses. Again, this is just to get rid of this here, and this b squared up front here. So yeah, just divide b squared, multiply b squared into here, and you get this. And I distribute these 2's in the numerator into the denominator here. So then I just move this over to the right side. So you see I flipped these two terms here to make it switch signs. And we can say that these conditions or these equations are not true for all coordinate b, or coordinate x and y, but it is true for the boundary conditions. So if x squared and y squared equals plus or minus b, these will equal, or this will equal b squared, and this will equal b squared, and it'll be 2 minus 1, and it'll be basically, yeah, the equation will be true on the boundary conditions, basically. So then part B, we want to compare, we want to basically derive the mass flow for this equation, and then we want to compare it to this mass flow, and we're going to see that it's not the same and it's not right, basically. So integrate our given velocity profile of a differential area is for given flow direction, which in this case is a square surface that gives VZ average velocity. Take unnecessary terms out of the integration and use multiplied out form to found in part A. Okay, what? Okay, so A equals 4b squared, and that's because each side of the square equals 2b, because each radius, or yeah, x equals plus or minus b, so the total x direction equals 2b, y equals plus or minus b, so the total y direction equals 2b. So 2b squared equals 4b squared, or 2b times 2b equals 4b squared. Sorry. Yeah, so A equals 4b squared, and the formula for average velocity is the integration of velocity over the differential area divided by the area. And the differential area is just dx times dy. It's it's a simple shape in Cartesian coordinates, so it's pretty easy. It's just dx times dy. And the coordinate bounds are plus b to negative b, again, because the problem said those are the bounds, basically. And then basically you just want to do some algebra, which is really annoying. I would say probably do Wolfram alpha if you can, but I'll scroll by this somewhat slowly. And by the way, this divided by a, it cancels out when you go to mass flow, because to find mass flow you have to multiply the average velocity times the area again. So you don't really have to put this here, as long as you remember that you don't have to multiply it out in the mass flow, basically. So yeah, there's all the math for that, which is really annoying to do. So now mass flow rate equals rho times average velocity times a. And again, this a here shows that this will just cancel out, or this a from the average velocity will just cancel out. So yeah, basically you're just canceling these out, multiplying it by rho, and then you bring this 4 out to 16 over 19, get 16 over 36. And so our mass flow rate equals 0.4 repeating times this expression. And if we look at the mass flow it gives us 0.563, all of the same variable terms. And so we can see that our mass flow rate is 78.9% of the given mass flow rate. And so our mass flow rate's wrong, basically. So yeah, that's the end of the problem. If you have any questions, please comment. If you have any suggestions for the channel, please comment. If you want me to do any specific problems in the book, please comment about that. Otherwise, have a good day. Bye-bye.